Freightliner trucks are built with precision on massive assembly lines. From steel frames and heavy-duty engines to intricate wiring and rugged cabins, every component is engineered for strength and reliability. Today, we go inside the factory to see how raw materials are transformed into powerful trucks that dominate highways and redefine modern transportation. Before the hum of torque wrenches or the hiss of pneumatic arms ever begin their synchronized dance, the production of a Freightliner truck starts much earlier at the material level. Freightliner, as a brand under Daimler Truck North America, sources its materials globally but manufactures domestically with an emphasis on high efficiency, high quality, and lean production methodologies. In practice, that means every component, from the massive frame rails to the smallest electrical connectors, follows a strict protocol from the moment they're commissioned. The backbone of every Freightliner truck is its chassis, and that begins with the steel. High-strength, low-alloy steel, engineered specifically to provide structural rigidity while reducing weight, is delivered in massive coils or long billets. These raw materials are typically sourced from certified mills across the US and Canada. Each shipment comes with metallurgical certification to ensure the proper carbon content, tensile strength, and fatigue resistance required for heavy load applications. Once the steel arrives at the plant or designated fabrication facility, it undergoes an initial inspection. Visual checks confirm the absence of surface defects like lamination or rust, while ultrasonic sensors or X-ray systems may be used for internal flaw detection. From there, the steel enters the cutting phase. Frame rails, the long backbone beams of the truck, are precision cut using CNC plasma or laser cutting systems. These machines follow CAD-generated paths to carve out the exact dimensions needed, often with tolerances down to fractions of a millimeter. Automated feeders load each steel section onto rollers, feeding them beneath gantry-style cutting heads. Sparks fly, not chaotically, but in orchestrated arcs of heat and light, as the steel begins to take its first identifiable form. But cutting is just the beginning. Each cut rail or cross member must be drilled, beveled, and punched to accommodate brackets, wiring looms, and other structural elements. These are done using robotic drill stations and multi-axis milling centers, often clustered in work cells that operate semi-autonomously. Workers oversee quality and handle any exceptions flagged by the system. It's not uncommon for a single frame component to pass through 8 or more stages of fabrication before it's ready for assembly. Meanwhile, in a different part of the facility, or sometimes an entirely different Tier 1 supplier plant, other key components begin their own parallel journeys. The cab, for instance, which forms the command center for the driver, starts its life as a series of stamped metal panels. These are formed in high-tonnage stamping presses, where flat steel sheets are fed into dies that exert upwards of 2,000 tons of pressure to form complex three-dimensional shapes. Roof panels, sidewalls, floor pans, and door skins are pressed, trimmed, and then moved into assembly cells for robotic welding. In one of the most mesmerizing stages of production, robotic arms, each about the size of a small car, move in choreographed unison, welding dozens of seams with astonishing precision. These are spot welds, placed at strategic structural points identified through finite element modeling simulations, ensuring the cab can withstand torsion, vibration, and frontal impact forces. The welding jigs are precisely machined, holding the panels in a fixed position to prevent warping and maintain dimensional accuracy. Each weld is logged, and sensors on the welding arms monitor heat, duration, and penetration in real time, ensuring every seam meets exacting standards. Once the skeleton of the cab is complete, it moves on to the paint line, though it's not quite time for color yet. First, the cab shell undergoes a rigorous cleaning and pre-treatment process to prevent corrosion and promote paint adhesion. This includes an alkaline wash to strip oils and residues, followed by a zinc phosphate bath that chemically prepares the metal. After that, the cab is electro-coated. In this process, the entire cab is submerged into a tank filled with electrically charged paint particles. A voltage is applied, causing the paint to be uniformly attracted to every surface, even inside the seams and cavities. This e-coat layer is critical. It forms a rust-resistant shell that will protect the truck for years, even in the harshest environments. While the steel skeletons are being formed and treated, the plastic and composite parts that will furnish the truck's interior and aerodynamic exterior begin their own fabrication process. Instrument panels, bumpers, fender extensions, and fairings are typically made using injection molding. Heated polymer resin is injected into steel molds under high pressure, then cooled and ejected, forming parts that are lightweight, durable, and dimensionally stable. These components are trimmed, drilled, and sometimes pre-painted before being cued for final assembly. The engine, the heart of the Freightliner, is usually sourced from Detroit Diesel, another subsidiary under the Daimler Truck umbrella. Engines such as the Detroit DD13, DD15, or DD16 are manufactured in parallel production lines, where aluminum engine blocks are cast, machined, and built up through a layered process involving crankshaft installation, piston assembly, cylinder head mounting, fuel system integration, and finally the addition of sensors, electronic control modules, and turbochargers. Each engine undergoes a hot test, where it's fired up and run under load conditions before it ever ships to the truck assembly plant. Transmissions and axles, often sourced from Eaton or Detroit Axle, are built in similar fashion, tested, and then sent in just-in-time batches to the Freightliner facility. Inventory control is tightly managed. Freightliner follows a lean manufacturing strategy, meaning parts arrive in closely timed windows based on actual production schedules. This minimizes storage needs on site and keeps the factory floor clear and efficient. By now, dozens of subsystems are in progress across multiple areas. Wire harnesses are being measured, cut, and terminated using automated cable cutting machines. Instrument clusters are assembled on dedicated benches with modular electronics, and HVAC systems are pre-tested on standalone rigs. Even the seats, often custom ordered based on customer specifications, are being upholstered, stitched, and fitted with safety sensors and air ride mechanisms. Each of these elements, whether it's a 900-pound axle or a palm-sized switch, will soon converge on a single assembly line, but that's still to come. First, all subcomponents must undergo quality control checks. Engineers and inspectors use a mix of digital calipers, laser measuring systems, and coordinate measuring machines to verify dimensions. Electrical systems are continuity tested using automated probes, while air and hydraulic systems are pressure tested for leaks. Any deviation from spec is logged in a centralized manufacturing execution system, or MES, which tracks every part from cradle to completion. The MES is the digital backbone of Freightliner's production philosophy. Every cab, frame, and engine has a digital birth certificate, a file that accumulates every test, measurement, and torque spec as it moves through the line. This level of traceability allows Freightliner to not only ensure consistent quality, but to rapidly isolate and correct defects if issues ever arise in the field. At this point, with thousands of parts flowing in from dozens of stations, the stage is set. The real magic, the assembly line itself, is about to begin. This is where human skill and machine precision merge in a seamless ballet of bolts, wires, and rivets, where every 12 minutes, a completed Freightliner truck rolls off the line, ready to shoulder the burden of logistics across a continent. But the choreography that makes that happen is anything but simple. As the curtain rises on the main assembly line, the factory enters its most synchronized and visually striking phase. The rhythm of production is guided by what's known in manufacturing as tak-T time, the calculated beat that determines how long each station has to complete its task. For Freightliner, depending on the model and plant configuration, a new truck might be rolling off the line every 10 to 15 minutes. But behind each of those trucks is a sequence of over 500 carefully choreographed steps involving hundreds of skilled workers and dozens of robotic assist systems. It all begins with the bare chassis rails, two long beams of hardened steel that form the skeletal spine of the truck. These rails arrive from the fabrication zone on heavy-duty conveyor systems. Before they even reach the first assembly station, they are scanned for orientation, Idaho, verified via barcode, and inspected by vision systems to ensure all required holes, cuts, and fasteners are present. Then, they're placed onto mobile build carriers, massive, gear-driven fixtures that move the entire truck frame down the line at a precise, constant pace. These carriers can rotate and tilt the frame slightly, allowing technicians ergonomic access to areas that would otherwise be difficult to reach. The first phase of assembly is focused on the undercarriage, namely installing the axles, suspension systems, crossmembers, and mounting brackets. A fully loaded Freightliner may be designed to support up to 80,000 pounds of gross vehicle weight, so the frame must be fortified to handle these loads with absolute reliability. Workers install steel cross members, bolted or riveted perpendicular between the chassis rails to enhance structural rigidity and prevent torsional twisting. Next comes the installation of the front and rear axles. Depending on the model, this could be a tandem axle configuration or a single drive axle for lighter duty vocational trucks. Each axle, pre-assembled with hub bearings, brake components, and wheel ends, is hoisted into place by overhead gantries equipped with hydraulic grippers. These assistive lifting devices are guided by technicians who carefully lower the multi-ton axle into position beneath the chassis rails. Once aligned, brackets and U-bolts are torqued down using calibrated pneumatic tools, each fitted with torque sensors to ensure fasteners meet the manufacturer's precise specifications. At the same time, the suspension system is installed. For most long-haul Freightliners, this means an air suspension setup where heavy-duty airbags, connected to leveling valves, are mounted in tandem with shock absorbers and trailing arms. These systems are designed to not only provide a smoother ride for the driver, but to protect the cargo from vibration and impact damage over long distances. Airlines are routed and clipped into place, and the system is pre-pressurized to check for leaks and integrity before moving to the next station. The steering system, too, is beginning to take form at this stage. Steering gearboxes are bolted to the frame and connected via linkages to the front axle. These components, although not yet connected to a steering wheel, are functional and mechanically aligned. Meanwhile, brake lines, often color-coded and routed through stainless steel conduits, are laid out along the chassis and secured at regular intervals. These lines will eventually connect to air reservoirs and electronic braking modules, which will manage the truck's braking system with a combination of mechanical and computer-assisted precision. As the frame grows in complexity, so too does the pace of integration. Fuel tanks are installed using insulated saddles and steel straps. These tanks, usually aluminum for weight savings, are pre-tested for leaks before arriving at the line. DEF tanks, used in modern emissions systems for diesel engines, are added alongside them. In vocational trucks like dump trucks or cement mixers, auxiliary hydraulic systems may also begin installation at this point, including reservoirs, pumps, and control valves. While this underframe activity unfolds, the cab is progressing down a parallel sub-assembly line. The painted cab shell, fully E-coated and prepped, is moving through its own series of workstations where interior components are being added. First, the wiring harnesses, pre-assembled bundles of electrical cable with color-coded insulation and printed tags, are laid into place. These harnesses control everything from the instrument cluster and lighting to the HVAC system and advanced driver assistance systems. Next, the dashboard is installed. This large composite structure comes pre-populated with electronic modules, venting ducts, and sometimes even gauge clusters, depending on the configuration. The HVAC unit, assembled separately and pre-tested in an environmental chamber, is mated behind the dash with refrigerant lines and vacuum-actuated dampers. Meanwhile, sound insulation panels are installed across the firewall and floor pan. These include layered composites of foam, mass-loaded vinyl, and aluminum shielding to reduce road and engine noise in the cab. Seats are installed next. Air ride driver seats with integrated heating, lumbar support, and, in some cases, electronic adjusters. These are bolted into pre-threaded inserts in the cab floor, and once secured, connected to wiring and air supply lines. Overhead control panels, sun visors, storage compartments, and sleeper modules begin assembly as the cab continues moving. Even interior trim pieces, such as door panels, kick plates, and A-pillar covers are clipped into place at this point. Every screw, every clip, every surface must pass tactile and visual inspection by quality technicians trained to detect the slightest deviation. With the cab interior nearly complete and systems verified for fit and function, it's now ready for what's known as the cab-to-chassis marriage. This is one of the most complex and dramatic moments in the entire production sequence. The cab, hoisted on a precision gantry crane, is slowly lowered onto the rolling chassis. But this isn't a blind placement. Alignment pins, laser positioning sensors, and human guides all play a role in ensuring the cab lines up perfectly with mounting points, firewall openings, and wiring pass-throughs. As the cab settles onto its mounts, typically a mix of rigid and elastomeric bushings to absorb vibration, technicians bolt it down using automated torque tools. Simultaneously, they connect the main electrical interface harnesses between the cab and chassis. These waterproof, high pin count connectors handle everything from turned signals and headlamps to engine controls and CAN bus data networks. Airlines for the braking and suspension systems are also routed from the chassis bulkhead into the cab via quick connect fittings. The steering column is connected to the steering gear via a collapsible intermediate shaft, and the parking brake cable is attached to its actuator. At this point, the truck is now beginning to resemble its final form. The integration of cab and chassis transforms a scattered system of components into a singular, rolling vehicle platform. And with this critical milestone complete, the truck moves into the fluid fill and powertrain test zones. But before that, another major piece must be installed: the engine and transmission assembly. Unlike consumer vehicles, where engines are often installed early in the process, Freightliner trucks receive their fully dressed engines after the chassis is partially assembled. The engine transmission module arrives as a single unit mounted on a subframe, complete with turbochargers, accessory drives, exhaust manifolds, and cooling modules already attached. This assembly is lifted into place using robotic hoists, aligning with the engine cradle on the chassis. Mounting bolts are inserted and torqued down in a specific sequence to prevent frame distortion. The drive shaft, a multi-section tube with U-joints and center bearings, is connected between the transmission output and rear axle input flange. Electrical connectors, fuel lines, coolant hoses, and air intake ducts are routed and secured. From this point forward, the truck is now considered live. It contains its engine, electrical backbone, braking systems, and operational suspension, but it's far from ready to drive. A battery module installed in steel trays along the side or rear of the frame is connected and charged. Now, the vehicle can begin low-voltage diagnostics and internal system checks. The cooling module, radiator, intercooler, fan shroud, and transmission cooler is installed as a pre-assembled front-end module. This module is bolted to the front of the frame and connected to the engine via hoses and mounting brackets. Charge air ducting for turbocharged models is secured using high-pressure clamps. The HVAC condenser is integrated into this module as well, bringing together thermal management for both engine and cab. Now, with all major modules mounted and cab systems connected, the vehicle enters the fluid fill station. Here, automated filling systems inject precisely measured amounts of engine oil, coolant, transmission fluid, brake fluid, and power steering fluid. Each system is pressurized and monitored for leaks. Sensors detect flow rate, air bubbles, and fill level in real time. If any irregularity occurs, the process halts automatically, and a technician is dispatched to correct the issue before moving on. Now that the Freightliner truck has its full frame, drivetrain, cab, cooling system, fuel and air systems, and operational electrical circuits, it enters one of the most sophisticated and diagnostically intensive areas of the entire plant, the calibration and alignment zones. Here, machines begin to speak to machines, and software begins to take control. The first step is a power-on diagnostic. With the battery system now live and the truck's electrical backbone fully connected, technicians initiate the onboard computer systems. This includes the engine control module, transmission controller, ABS module, airbag control unit, body control module, and telematics gateway, among others. At this moment, the truck boots up, like powering on a small data center on wheels. A handheld or overhead diagnostic interface is connected to the vehicle's onboard diagnostic port. This interface communicates with the entire network of controllers using protocols like SAE J1939 and KN bus. The technician initiates an automated diagnostic sequence that verifies communication with all electronic modules. If any controller fails to respond or reports a fault code, the process halts, and the vehicle is flagged for further investigation in a rework bay. Otherwise, it proceeds to electronic calibration. Calibration is a critical process that sets each truck's electronics to match its unique configuration. No two trucks rolling off the line are exactly alike. One may be a day cab designed for regional haulage, while another might be a sleeper cab configured for coast-to-coast operations with collision mitigation systems and adaptive cruise control. The calibration process loads the correct firmware and parameter sets into each module, ensuring that systems like automatic transmissions shift appropriately for axle ratios, or that driver assistance systems are aware of wheelbase length and sensor positions. This is done via secure upload stations, where each truck is assigned a digital build sheet linked to its VIN. The calibration software retrieves this data from the central MES system and programs each controller accordingly. The parameters include everything from fan clutch engagement temperatures to PTO behavior and idle shutdown timers. Once complete, each module reports back its configuration status, and the entire vehicle is now digitally aligned to its physical build. Next, the vehicle moves into the alignment station. Heavy-duty laser alignment systems, mounted on rails or fixed towers, are used to measure the orientation of the front steering geometry and rear axles. Unlike passenger vehicles, trucks often have multiple axles that must be precisely aligned, not just for handling, but for fuel economy and tire wear. Toe, camber, and thrust angles are all checked in real time. Technicians use alignment racks, where the truck is driven or pushed onto a set of turntables and sensors. The wheels are clamped with reflective targets or optical sensors, and the alignment rig projects laser beams to calculate angles down to fractions of a degree. Adjustments are made on the spot, typically by rotating tie rods or adjusting shims, until all values fall within Freightliner's tight specifications. With alignment complete, attention turns to tire and wheel torque verification. Even though wheel and tire assemblies were installed earlier, every lug nut is now checked using either digital torque wrenches or wheel torque verification robots. These tools not only confirm that each nut is tightened to specification, but they record the actual torque value in the MES system. tying it permanently to that truck's build history. Any deviations are logged, and the operator must reperform the torque sequence until it passes. The vehicle now proceeds to what is perhaps one of the most dramatic stations in the entire factory, the rolling test bay. These bays simulate real-world road conditions using massive rollers embedded in the floor. The truck is driven or guided onto the rollers and secured in place using heavy chocks and hydraulic clamps. The goal is to test engine performance, transmission shifting, braking behavior, and electronic stability systems in a controlled environment. A technician enters the cab and starts the engine. Diagnostic software monitors over 1,000 real-time data points while the truck is run through a series of controlled cycles. The accelerator is gradually pressed, spinning the drive wheels up to simulated road speeds. The automatic transmission is monitored to ensure proper gear changes. The ABS is triggered under simulated braking, verifying sensor input and control module logic. While the truck is driving in place, exhaust gases are routed through a ceiling-mounted emissions probe. This system continuously analyzes the output for nitrogen oxides, carbon monoxide, hydrocarbons, and particulate matter. The truck's aftertreatment system, which includes diesel oxidation catalysts, diesel particulate filters, and selective catalytic reduction modules, is monitored to confirm that emissions stay well below EPA and CARB limits. At the same time, the system also confirms that the engine software is not modified, tampered with, or otherwise non-compliant. This is done using secure electronic handshake protocols between the ECM and the test equipment. Once the rolling test is complete and all values fall within acceptable limits, the vehicle proceeds to the leak and pressure test station. This station tests all air systems for integrity, including air brakes, air suspension, and air horn systems. The truck is parked, and the air tanks are fully pressurized using either the onboard compressor or an external air source. Sensors monitor the system for pressure decay, typically looking for less than a 2 psi drop over a fixed time window. If the system passes, it is deemed leak-free. If it fails, it is routed to a diagnostic bay for smoke testing or manual inspection. Similarly, the HVAC system is tested for refrigerant charge and performance. A technician activates the air conditioning and heating functions while monitoring the vent outlet temperatures. This ensures that the climate system is operating within spec before the truck is shipped. Even the windshield washer system is activated, and fluid reservoirs are topped off as needed. Now, nearing the final phase of the build, the truck enters the fit and finish inspection zone. Here, the human eye and hand still reign supreme. While automation excels at measuring torque and electrical signals, it takes trained inspectors to detect cosmetic defects, misaligned trim, or imperfect panel gaps. Workers walk around each truck with checklists in hand, inspecting everything from door seals and mirror mounts to paint finish and decal placement. The doors are opened and closed to check for proper latching. The cab lights, headlights, turn signals, brake lights, and reverse lights are all tested. The horn is honked, the wipers are activated, and the radio is briefly turned on to verify speaker operation. For trucks with sleeper cabs, technicians crawl into the bunk area and test interior lighting, power outlets, and optional features like inverters or bunk HVAC units. If the truck passes all these visual and functional checks, it's moved into the detailing area. Here, protective films applied earlier in the assembly process are removed. The cab and chassis are wiped down to remove any assembly dust or handprints. Paint is polished if necessary, and tire shine may be applied for customer delivery presentation. As the truck sits, gleaming under overhead lights, it's finally ready for what's called a road-ready release. A final supervisor, often with years of experience, performs one last walk-around, signing off on the truck's build sheet. This triggers the MES system to mark the unit as complete, at which point a unique certificate of conformance is generated. This document certifies that the truck meets all Freightliner build standards, federal safety regulations, and emissions compliance requirements. To understand the making of a Honda Civic, we must start long before the wheels ever touch asphalt. At the very genesis of the production journey, the press shop. It is here, in a thunderous hall lined with towering metal-forming presses, that raw coils of rolled steel arrive from trusted suppliers. These steel coils, typically delivered on massive trucks or freight trains, are carefully quality checked for thickness, tensile strength, and surface consistency. Technicians inspect the incoming steel with precise ultrasonic and magnetic sensors, looking for any hidden flaws that might affect structural integrity. Once verified, the steel coils are loaded onto an unwinding line and fed into massive blanking presses, machines that slice sheets to exact dimensions for body panel stamping. This stage is not about shape yet. It's about preparing the right size of metal blanks that will later be contoured into the Civic's recognizable exterior components. Each blank is fed robotically into a deep draw stamping press, some of which exert more than 2,000 tons of force in a single downstroke. These presses contain die sets, essentially giant molds machined to micrometer tolerances, which shape the flat blanks into complex three-dimensional parts: doors, hoods, quarter panels, floor pans, and roof skins. The stamping process is both violent and elegant. With each press cycle, a blank disappears between the dies, emerging seconds later with ridges, folds, and curves now embossed into the once flat steel. Robotic arms then transfer these parts to stacking racks with vacuum grippers, organizing them for their next destination, the body shop. If the press shop is the forge, the body shop is the sculpture studio. It's here that the Civic begins to take on its distinctive silhouette. Using a mix of robotic welders, jigs, and human technicians, the various stamped body panels are aligned with incredible precision. Fractions of a millimeter make all the difference in structural rigidity and door fitment. The underbody is constructed first. Floor pan, frame rails, and cross members are robotically welded together in massive fixtures that hold them square. These sub-assemblies are then mated with the upper body structure, including the firewall, roof bow, and side panels. The process of joining these panels together is an art form in itself. Honda uses a combination of spot welding, where copper-tipped electrodes pass current through panels to fuse them, and laser welding, which offers even greater strength and less distortion. Each Civic contains thousands of spot welds, each one measured by inline sensors for penetration, pressure, and temperature. In certain areas, structural adhesives are also applied robotically before parts are pressed together, increasing torsional stiffness and reducing vibration. As the body shell, now called the body in white, progresses through the line, it moves through various stations where more components are added: inner reinforcements, mounting brackets, and crash structure members. Robots ensure these parts are always placed in precisely the same position on every vehicle. The body is then passed through a computerized vision inspection system, which scans it in real time for dimensional conformity. If anything is off, even by a millimeter, it is flagged and corrected immediately. With the body in white completed, the Civic now advances to one of the most critical and carefully controlled areas in the factory: the paint shop. Before any color can be applied, the raw steel must be prepared with a meticulous cleansing process. The car shell is first subjected to a multi-stage bath sequence in giant dip tanks that use alkaline detergents to remove oils, dust, and microscopic particles left over from stamping and welding. The shell is rotated robotically through each tank, allowing it to be completely submerged and ensuring even coverage across all surfaces, both exterior and hidden interior cavities. After cleaning, the body enters an e-coat bath, short for electrophoretic deposition coating. In this step, the shell is electrically charged and dipped into a tank filled with a water-based primer containing corrosion-inhibiting particles. The electrical charge causes the primer particles to be attracted and evenly bonded to the body's surface. This layer not only improves paint adhesion, but provides crucial rust protection, especially in inner cavities that are hard to reach with spray guns. Once the E-coat is cured in an oven at around 180 degrees Celsius, the Civic moves into the primer application booth, where robotic arms spray a base primer coat across the shell. This step evens out the surface texture and prepares it for color paint. Following a short curing phase, the vehicle is moved into the color booth, a climate-controlled, dust-free chamber where the final paint coat is applied. Each Civic model has its own unique paint codes, which are carefully loaded into robotic arms that spray layer upon layer of base coat and clear coat in a highly choreographed dance. The painting process is arguably one of the most mesmerizing stages to witness. 12-axis robotic arms glide effortlessly around the car body, their movements pre-programmed down to the millisecond, ensuring consistent paint thickness and flawless coverage. The color coat is followed immediately by a layer of clear coat, which adds depth and gloss while protecting the finish from UV light and environmental damage. After curing in a second oven for up to 40 minutes, the freshly painted Civic body emerges gleaming, but still empty. Just a hollow shell with no glass, no engine, no wheels. That's about to change. The next phase, is the trim and chassis marriage line, where the Civic's raw body begins to transform into a fully outfitted vehicle. This is where thousands of individual parts, from wiring harnesses to dashboard assemblies to seatbelt retractors, are installed piece by piece, each in a strictly orchestrated order that has been optimized for both ergonomic efficiency and production speed. Before any of that happens, however, the body must be precisely prepared for the installation of glass. Robots apply urethane adhesive beads around the front and rear window openings, and then suction-equipped robotic arms carefully position and press fit the windshields and back glass into place. Smaller fixed windows are installed similarly. These adhesives not only secure the glass, but also provide structural rigidity and watertight sealing. Inside the cabin, the assembly line team begins installing sound-deadening mats, interior wiring looms, dashboard subframes, HVAC ducting, and insulation panels. Every cable must be routed correctly through predefined paths using color-coded guides and clips to avoid interference or rattling. Robots and technicians work side by side. Robots handling repetitive or awkward tasks such as bolting down seat frames or placing door wiring clips, while humans complete more dexterous jobs like feeding dashboard harnesses through tight spaces. In a parallel part of the factory, just as precise and choreographed as the main body line, the powertrain assembly line is busy bringing together the mechanical heart of the Honda Civic. Here, in a series of carefully timed workstations, the engine block, cast from aluminum alloy at an off-site foundry, is delivered for the beginning of what will become a highly intricate construction process. The raw engine block, a silvery rectangular core with machined bores and passages, is first mounted to an adjustable rotating stand that allows technicians and robots to access all angles of the component with ease. Technicians begin by installing the crankshaft, main bearings, and connecting rods, each component measured to precise tolerances using torque wrenches and digital sensors. The pistons are inserted and aligned with the cylinders, lubricated and checked for correct seating before the cylinder head is mounted and bolted down in a strict torque sequence. Fuel injectors, spark plugs, oil pans, gaskets, and camshafts are all installed in sequence. Robotic arms place timing chains or belts, set cam phasing, and verify timing alignment using vision inspection systems that reference QR codes and part markings. Once complete, each engine goes through a cold test station where sensors check oil circulation, compression ratios, and component tolerances without actually firing the engine. If the unit passes, it continues down the line to be joined with the transmission, either a continuously variable transmission, 6-speed manual, or in some markets, a traditional automatic. These transmissions arrive from specialized Honda transmission plants and are pre-assembled with clutches, gears, and hydraulic valve bodies already in place. The marriage of engine and transmission is done with the help of alignment jigs and torque-monitored bolt drivers to ensure perfect balance and alignment. This combined powertrain module is then sent via automated guided vehicle to the chassis line, where other sub-assemblies, such as the front subframe, suspension arms, steering rack, and exhaust system, are already being built up. In this stage, the Civic's front and rear subframes are assembled separately, each housing the relevant suspension geometry, control arms, sway bars, and dampers. These are pre-torqued and inspected before being mated to the powertrain and chassis cradle. Once this fully assembled underbody unit is complete, it moves via overhead conveyor to the marriage station, a dramatic intersection of the trim line and the chassis line. The painted body shell, with dashboard and interior partially installed, is suspended above the cradle. Slowly, the two converge. Using laser guidance and a complex hydraulic lift system, the car body is lowered onto the powertrain module with millimeter precision. Specialized guide pins ensure perfect alignment, and robots immediately begin bolting the chassis and body together at multiple mounting points. This process, known as the body drop or marriage, represents one of the most pivotal points in the Civic's construction. In just a few minutes, the car transitions from a hollow shell to a complete vehicle with drivetrain, suspension, and steering components now integrated. From here, the assembly line continues with intense precision as the Civic begins to come alive, inch by inch. The next station involves connecting electrical harnesses and fluid lines. Large modular connectors are snapped into place, linking the vehicle's main computer systems, ECU, sensors, transmission control, and lighting. Brake lines, fuel hoses, coolant pipes, and air conditioning refrigerant lines are connected with quick coupling fittings that are color-coded and pressure-tested for leaks. Robots insert and fasten fuel tanks underneath the chassis, followed by heat shields and underbody panels that protect the car's systems from road debris and temperature extremes. Meanwhile, technicians inside the vehicle are installing the instrument panel, infotainment system, airbag modules, and steering wheel. The center console and infotainment head unit are test-fired on the spot, using a temporary power source to ensure all touchscreens, audio systems, and onboard diagnostics are functional. Seats arrive pre-assembled from a separate supplier and are robotically positioned, bolted down with monitored torque drivers, and electrically connected for airbag and heater functions. Simultaneously, the doors, which were removed earlier in the process to improve access during interior assembly, are now reattached by a series of 6-axis robots. These machines lift the doors from their carriers, align them to body datum points, and bolt them onto reinforced hinges with a precision that's been pre-calibrated using 3D body scans taken earlier. Technicians then install seals, trim pieces, weather stripping, and window regulators before the power windows are connected and tested electronically. Next comes the installation of exterior lighting. Headlamps and taillights are snapped into place with molded brackets, fastened with screws and bolts, and connected via waterproof electrical connectors. Each light module is briefly illuminated to confirm functionality and correct alignment. The front grille, bumper fascias, and underbonnet components, such as the air intake ducting, battery, and fuse boxes, are added next. Every step in this stage is monitored in real time by a central production server that tracks torque readings, scan codes, and pass/fail diagnostics from every tool on the line. With nearly all physical components in place, the Civic is almost complete. but not quite ready to leave the line. Next, the wheels and tires are installed. Tires arrive from Honda's tire supplier, already mounted and balanced on alloy wheels. They are indexed and attached to the hub assemblies using robotic wheel guns calibrated to apply the exact torque specification for each lug nut. These specs vary depending on wheel size, market, and drivetrain layout. An automated alignment station immediately follows, where high-speed cameras and laser sensors measure and adjust toe, camber, and caster angles on all four wheels. These adjustments are performed automatically by robotic arms that adjust the suspension linkages without human input. The engine is now ready for its first breath of life. The car is filled with all necessary operational fluids: engine oil, transmission fluid, coolant, windshield washer fluid, brake fluid, and refrigerant. These fluids are dispensed using automated boom systems that identify the vehicle model via RFID tags and fill to precise volumes using flow sensors. Then, the Civic moves into the initial startup bay, where for the first time, its ignition is triggered. An onboard computer runs a rapid series of checks on fuel pressure, ignition timing, emission systems, and electrical networks. If any error code is flagged, the vehicle is diverted for diagnostics. If everything checks out, the Civic proceeds. Following startup, the vehicle undergoes a dynamic rolling test on a set of inline dynamometers. The car's wheels are driven at varying speeds while technicians monitor acceleration, braking, gear shifting, and engine response. Noise, vibration, and harshness levels are recorded using microphones and vibration sensors in key areas. The vehicle's radar, sonar, and camera-based safety systems, like lane keeping assist and adaptive cruise control, are also calibrated using test targets and moving objects. Even the horn and windshield wipers are tested as part of this comprehensive validation. Once mechanical systems are signed off, the Civic advances to the water test booth, an enclosed tunnel fitted with high-pressure nozzles simulating rain and storm conditions. The car is sprayed for several minutes from all angles to ensure no water leaks into the cabin or trunk. Any intrusion, however slight, results in the vehicle being pulled for resealing and retesting. After the water test, the Civic passes through the final inspection bay. Here, a team of trained inspectors examine every surface of the car under bright, full-spectrum lighting to detect paint imperfections, panel misalignments, or blemishes. Doors, hoods, and trunks are opened and closed repeatedly to confirm proper fit and latch operation. Interior materials are checked for stitching quality, switch function, and material alignment. Even the scent of the cabin is evaluated to ensure consistency with Honda's brand standards. Once it clears final inspection, the Civic is driven briefly to a short holding area where any software updates are flashed into the ECU, infotainment system, and onboard diagnostics. The vehicle's VN is laser etched into the frame and stored electronically in Honda's global database. The car is now officially considered production complete. With the vehicle officially signed off from the production line, the next phase of the Honda Civic's journey is handled by a specialized logistics team responsible for organizing and staging vehicles for transport. At this point, every Civic has its final configuration, its color, trim level, engine variant, transmission type, and region-specific features all set in stone. But before it's shipped off to a dealership or distribution hub, it enters what's known as the Vehicle Outbound Logistics System. In a vast open-air vehicle yard adjacent to the assembly facility, often spanning hundreds of acres, you'll find hundreds, even thousands, of freshly minted Honda Civics parked in rows that stretch toward the horizon. This yard is not simply a parking lot, it's a tightly managed inventory control zone that functions like a living spreadsheet. Each Civic is tagged with an RFID chip or barcode label that links to a digital manifest. These digital profiles contain everything about the vehicle: where and when it was built, its VIN, trim level, market destination, port of discharge if being exported, and even its assigned dealership. Before entering this staging area, each vehicle is given a final scan at the gate. This scan confirms the completion of software installation, quality checks, and fluid top-offs. Once scanned, a logistics automation system assigns a parking spot based on the vehicle's outbound path. Cars, headed for rail transport, are parked near the loading tracks. Those bound for container shipping are staged by the dock ramps. Regionally distributed vehicles are positioned near road freight terminals. Each parking operation is choreographed with the help of a fleet of vehicle movers, some human, some automated. In newer facilities, autonomous electric tugs shuttle completed cars to their assigned staging rows, minimizing fuel usage and reducing human error. As the Civic arrives at its designated position, it is double-checked for cosmetic integrity. No scratches, no dents, and no contaminants like bird droppings or sap that could damage paint before delivery. Depending on the region, the vehicle may receive a light protective wrap, plastic sheeting on the hood, roof, and doors, as well as foam bumpers or wheel covers. These additions protect the finish during transport, particularly when Civics are being shipped across long distances via rail or ocean freight. From here, distribution diverges based on geography. Civics bound for nearby regions are typically loaded onto multi-level auto transport trucks, known as car haulers, using a hydraulic ramp system that maximizes vertical space. Each trailer can accommodate 8 to 10 vehicles, depending on size and configuration. Loading these haulers is a skillful job. Drivers must navigate tight clearances, especially when reversing a Civic up a narrow ramp just inches from another car's bumper. Once secured, the transport trucks depart along pre-planned routes, tracked in real time with GPS and monitored for weather, traffic, and delivery schedules. Vehicles typically arrive at regional distribution centers or directly at dealerships within 24 to 72 hours of departure, depending on distance. But for Civics headed overseas, the process is even more elaborate. Vehicles scheduled for export are transported to a port of exit, usually via rail. Special rail cars, called autoracks, are designed for this purpose. They're 3 levels high and feature secure wheel chocks, enclosed sides to protect from the elements, and locking mechanisms to prevent vehicle movement during transit. Before boarding the train, each Civic goes through a brief pre-rail inspection, checking tire pressure, door latches, and fuel levels. Vehicles must carry just enough fuel for loading and unloading, nothing more. Once the autoracks reach a port, often within a few days, the Civics are offloaded and prepped for ocean shipping. At the port, Honda works with marine logistics providers to board the vehicles onto roll-ons or roll-off vessels. These are essentially floating parking decks that can carry thousands of cars at once. A team of stevedores and vehicle handlers drives each car onto the ship via massive loading ramps. The cars are parked tightly together, locked down with wheel straps, and catalogued by location and destination. Each ship carries a mix of vehicles headed to different global markets, with each deck subdivided by destination. During the sea journey, which can last anywhere from 2 to 6 weeks, depending on the destination, the vehicles remain dormant but protected. Temperature, humidity, and salt exposure are controlled to prevent corrosion. Some ships use dehumidification systems to further protect sensitive electronics and cabin components. Upon arrival at the destination port, be it Vancouver, Rotterdam, Sydney, or Tokyo, the Civics are offloaded and moved to an inbound vehicle processing center. Here, local Honda representatives carry out market-specific inspections and final preparations. Depending on regulations and consumer preferences, some components may be installed at this stage. Market-specific infotainment systems, badges, labels, or compliance stickers. The battery is checked, tire pressure adjusted for the regional climate, and the vehicle is detailed one final time. Then, and only then, does the Civic make its final trip to a dealership, where it will be test-driven by prospective buyers and eventually become part of someone's daily life. The journey from raw steel coil to showroom floor is now complete. But behind this process is something even more impressive than the car itself: the manufacturing ecosystem that made it all possible. Every Honda plant, whether in Canada, Japan, the United States, or Thailand, is a model of lean manufacturing. Honda is one of the pioneers of flexible assembly, meaning the same line that produces the Civic may also produce other models with minimal downtime between them. This flexibility allows the plant to respond to shifting market demands without reconfiguring the entire factory. The chassis platform used by the Civic, for instance, might also underpin the Honda HR-V or Insight, all of which can be built on the same line with different modules and components swapped in real time. This orchestration relies on an advanced system of just-in-time supply chain logistics. Rather than stockpiling parts on-site, Honda's suppliers deliver components like dashboards, seats, HVAC modules, and wiring harnesses exactly when they're needed, often arriving at the plant just hours before installation. This minimizes inventory costs and allows for rapid changes to production volume or specification. Each component comes pre-labeled with a digital build sheet that identifies exactly which Civic it's meant for, ensuring flawless sequencing on the line. Complementing this is the just-in-sequence system, which goes one step further, delivering parts in the precise order of vehicle production. For example, if the assembly line is building a red Civic Sport, followed by a blue Civic X, the bumpers, headlights, and infotainment units for each car arrive in that exact order, pre-arranged for immediate installation. It's a ballet of logistics that requires real-time communication between Honda's central production servers and hundreds of Tier 1 and Tier 2 suppliers. To keep everything running smoothly, predictive maintenance is used throughout the plant. Equipment sensors track vibration, temperature, load, and wear in everything from conveyor belts to robotic welders. When a part shows signs of fatigue, the system schedules preventative maintenance before failure can occur, reducing downtime and improving safety. Quality control doesn't end once a vehicle leaves the line. Each factory maintains a dedicated audit station where randomly selected Civics are pulled for intensive testing. These vehicles are dissected and reviewed by expert inspectors who examine weld quality, paint thickness, body fitment, software behavior, and road performance. This data is fed back into the production process to flag trends or emerging issues, enabling Honda to respond proactively and maintain consistent quality. In terms of environmental responsibility, Honda's Civic production lines are engineered for energy efficiency and waste reduction. Water used in the paint booth is recycled through filtration and reverse osmosis systems. Paint overspray is captured by electrostatic filters and reused. Waste metal from the stamping plant is sorted robotically and returned to the steel mill for remanufacturing. Even the heat from curing ovens is repurposed to warm other parts of the facility. Power consumption across the plant is closely monitored and managed. Many Honda facilities are partially powered by solar arrays, wind energy, or cogeneration systems. Advanced lighting systems using motion sensors and LED technology ensure that energy is only used when and where it's needed. In some plants, Honda has achieved near-zero landfill status, meaning almost all waste materials, plastic, metal, rubber, even food waste, are recycled or repurposed in some way. Inside the modern Honda manufacturing plant, what might seem like a chaotic tangle of machines, parts, conveyors, and workers is in fact a precisely engineered environment orchestrated with clockwork efficiency. At this stage of production, where physical assembly transitions into post-production optimization and system refinement, the focus increasingly shifts from brute force manufacturing to intelligent systems management, what Honda refers to internally as manufacturing excellence. At the heart of this excellence is automation, an ever-present, evolving backbone of the modern Civic factory. Over 60% of tasks on the assembly line are now completed or assisted by robots. These are not simple, one-purpose mechanical arms, but intelligent, adaptable systems equipped with high-resolution sensors, 3D cameras, and real-time process feedback. In the body shop, robotic welders do far more than spot weld. They monitor the pressure of each weld in milliseconds, analyze the depth of each fusion, and dynamically adjust parameters to compensate for slight variations in steel thickness or surface contaminants. These adjustments happen in real time, with hundreds of data points captured per second and logged directly into Honda's centralized manufacturing database. Each of these robots is not just a tool, but a node in a larger intelligent network. That network, Honda's digital production control system, is built to track every Civic as it moves through the plant. From the moment a steel blank enters the stamping press to the final torque applied to the last wheel nut, the vehicle's identity is logged and linked to a database of component specifications, supplier batch numbers, sensor readings, machine parameters, and quality checks. This system allows Honda to maintain traceability, a key principle in modern automotive manufacturing. If a defect is ever found in a Civic's transmission casing or infotainment unit, engineers can instantly trace that part back to the day, time, and exact supplier lot it came from. This level of insight allows for surgical product recalls rather than sweeping generalizations, and is a cornerstone of Honda's commitment to quality and customer safety. In many zones of the factory, cobots or collaborative robots are replacing traditional industrial arms. These are smaller, more agile machines designed to work side by side with human operators. Unlike traditional robots that are fenced off behind safety barriers, cobots use proximity sensors, pressure feedback, and vision systems to detect the presence of humans and respond accordingly. For instance, in the trim assembly zone, cobots might assist a technician by precisely positioning heavy dashboard modules while the human secures them in place with fasteners. This reduces operator fatigue and improves assembly consistency, particularly for ergonomically challenging tasks that are difficult to automate entirely. Even AGVs, or automated guided vehicles, have seen substantial evolution. No longer confined to fixed track systems, newer Honda plants use vision-guided or LiDAR-based AGVs that navigate the factory floor independently, rerouting in real time to avoid traffic congestion or bottlenecks. These intelligent carts move everything from seats and dashboards to windshield glass and wiring harnesses, all without human input. Each AGV is linked wirelessly to the central factory control hub, which orchestrates their movements in relation to production flow. They are programmed to deliver specific components to a station at a precise time, synchronized with the exact Civic model being assembled at that moment. And this synchronization is not theoretical. Honda employs a modular assembly system, meaning that various trim levels, powertrain variants, and color options are built on the same line, back-to-back, without downtime. A Civic Sport with manual transmission might be followed directly by a Civic Touring with a CVT and an entirely different dashboard layout. Each workstation is equipped with smart tools, torque wrenches that automatically adjust to the specification required for that trim, vision systems that verify part fitment, and pick-to-light component bins that illuminate only the exact part required for that vehicle configuration. The system dynamically adapts the line to each unique build without requiring tool changes or reprogramming. In areas such as windshield installation or seat alignment, machine vision systems play a critical role. High-definition cameras capture detailed images of each step in the process, comparing live data to reference models stored in the system. These cameras can detect misalignments as small as 0.2 millimeters and instantly alert workers or trigger robotic correction. If a deviation is beyond correction thresholds, the system flags the vehicle and diverts it to a diagnostic bay for human evaluation. These inline quality checks are far more than visual. They're statistical safeguards, using large data samples to spot trends before they become problems. The paint shop, often one of the most energy-intensive parts of the plant, has also embraced advanced automation. Honda's robots not only apply base coats and clear coats with micron-level consistency, they also self-monitor the viscosity of paint, adjust spray patterns for optimal atomization, and even self-clean their nozzles between cycles. Overspray, which historically represented significant waste, is now captured by electrostatic plates and returned to a closed-loop reclaim system. Humidity and airflow in the paint booths are adjusted in real time to compensate for changes in ambient conditions, ensuring flawless finish consistency across seasons and global regions. Underpinning all of this automation is a layer of predictive analytics. Honda doesn't just react to faults, it forecasts them. Every sensor, robot, conveyor, and torque gun in the plant feeds data into a centralized AI-driven platform that looks for anomalies. If a certain fastener is being torqued more tightly than normal over a series of builds, the system flags the deviation. It may indicate tool wear, part misfit, or an upstream supplier issue. Engineers are alerted before a failure occurs. This predictive maintenance approach has dramatically reduced downtime and improved first-pass yield, an industry metric referring to the percentage of vehicles that pass inspection without needing rework. In the engine assembly hall, torque sensors are so precise they can detect if a technician has even one thread of a bolt cross-threaded. If detected, the system locks the build station, highlights the error on a display, and prevents the engine from moving forward until the issue is addressed. These safeguards ensure that even as production volume increases, Honda maintains the reliability and consistency that the Civic name is built upon. Lighting across the factory is controlled by intelligent energy management systems. LED lights adjust brightness based on time of day, production activity, and occupancy, cutting power usage dramatically. Heating and cooling systems adapt to the number of people in a zone and the thermal load of nearby machines. Even compressed air systems used in pneumatic tools and robotic actuators are monitored for leaks. Any pressure drop triggers an alert and isolates the zone for maintenance. These efficiencies not only reduce environmental impact, but also contribute to cost savings that allow Honda to reinvest in manufacturing innovation. As Civic production continues around the clock, every process, every station, and every worker is part of a living, learning system. The factory itself becomes smarter with time. Lessons learned from one batch of Civics are automatically integrated into subsequent runs. And when a mid-cycle refresh or new feature is introduced, say a redesigned infotainment interface or new powertrain calibration, the change is implemented digitally across the plant. Robots are updated wirelessly with new motion paths. Technicians receive augmented reality instructions via tablet. Parts suppliers are given revised sequencing instructions within minutes. As the Honda Civic continues its evolution on the global stage, one aspect of its production has grown increasingly central to the company's mission: sustainability. Manufacturing a modern automobile like the Civic requires immense amounts of energy, materials, water, and logistics, all of which must now be managed under the pressure of carbon emissions reduction and environmental stewardship. Honda's response to this challenge has been far from superficial. In many ways, its Civic production lines have become test beds for the company's broader efforts in building low-impact, resource-efficient factories. Every modern Civic plant is built with environmental performance targets baked into its architecture. From the outset, Honda employs what it calls Green Factory Principles, a framework of metrics and strategies for reducing energy consumption, carbon footprint, chemical emissions, and waste. These principles are applied at every level, from site selection to machinery operation. One of the most visible aspects of this sustainability initiative is Honda's aggressive use of renewable energy sources. Several Civic production plants, such as the one in Greensburg, Indiana, use large-scale solar panel arrays to offset electricity usage. These panels are often installed on the roofs of buildings or in dedicated solar fields adjacent to the facility. While they may not yet power the entire operation, they significantly reduce reliance on fossil fuels and provide a stable energy source for specific systems like lighting grids or HVAC. In addition, some facilities make use of combined heat and power systems, also known as cogeneration units, which burn natural gas to generate electricity on-site while capturing waste heat to provide hot water and climate control. These systems can be more than twice as efficient as pulling electricity from the grid alone, significantly cutting greenhouse gas emissions per kilowatt hour used. But it isn't just energy that's optimized. Water usage is a critical sustainability issue, particularly in the paint shop, where thousands of liters are required daily for rinsing, cleaning, and chemical mixing. Honda's solution has been the implementation of closed-loop water recycling systems. These systems use a mix of ultrafiltration membranes, reverse osmosis, and UV sterilization to clean and recirculate water through the plant. In some factories, as much as 95% of water used in production is reclaimed and reused. The E-Coat dip tanks, for example, are now topped off with recycled water that meets near laboratory-grade purity standards. Chemical usage in painting and metal treatment processes has also been re-engineered. Honda has transitioned many of its surface preparation and cleaning solutions to low VOC and phosphate-free alternatives. This not only reduces hazardous waste, but also improves worker safety and air quality inside the factory. Ventilation systems are fitted with electrostatic scrubbers and HEPA filters to capture overspray particles and solvent vapors, reducing emissions that would otherwise enter the atmosphere. Solid waste is handled with equal intensity. Modern Honda Civic plants operate on a near zero landfill policy. That means virtually all manufacturing waste, scrap metal, plastics, rejected parts, packaging materials, even cafeteria waste, is sorted, recycled, or repurposed. Steel offcuts from the stamping shop, for instance, are collected automatically by magnetic conveyors and baled for return to the steel mill. Plastic injection molding runners are ground up on site and reintegrated into new parts. Waste lubricants are filtered and reused for non-critical applications. To track the progress of these initiatives, every plant maintains a real-time environmental dashboard, visible to both operators and management. This dashboard displays metrics like kilowatt hours per car produced, liters of water used per cycle, paint shop VOC emissions, and recycling rates. Engineers use this data to identify inefficiencies and launch Kaizen initiatives, small, continuous improvements that ripple across departments and compound over time. These dashboards are also shared across Honda's global factory network to spread best practices from one facility to another. That global network is itself a masterclass in distributed manufacturing. Unlike some automakers that rely on a single central plant for specific models, Honda's Civic production is distributed across multiple countries. This includes facilities in Japan, the United States, Canada, the United Kingdom, Thailand, and others depending on generation and market. Each of these plants is capable of localized production, a practice where the Civic is manufactured with regional suppliers, regulations, and consumer preferences in mind. For instance, Civics built for the North American market may feature different safety systems, infotainment options, or climate control calibrations than those produced for Southeast Asia or Europe. This localization reduces the carbon footprint of global shipping, lowers costs, and allows Honda to respond quickly to local demand. Supporting this decentralized system is a globally synchronized digital architecture. Through Honda's global production operations system, every plant can access standardized blueprints, torque specs, quality benchmarks, and real-time engineering updates. If a supplier in Thailand discovers a defect trend in a batch of brake calipers, that information is immediately shared across the entire network, triggering preemptive inspections in other factories and supplier audits if necessary. It's a powerful example of how data is now just as important as steel in car manufacturing. These global factories are also adapting to accommodate a rising wave of powertrain diversification. As demand for cleaner transportation grows, Honda has committed to electrification, not just in full EVs, but also in hybrid and plug-in hybrid variants. For the Civic line, this means that certain factories now have dual powertrain capability, allowing them to produce both internal combustion and hybrid electric Civics on the same line. This feat of integration requires major adjustments to logistics, assembly sequencing, and training. Hybrid Civics require the installation of battery packs, inverters, high voltage wiring, and regenerative braking systems, all components absent in a traditional Civic. These parts arrive from Honda's dedicated eDrive suppliers, or in-house battery module assembly units. Once in the plant, they are carefully synchronized with the hybrid vehicle builds using the same just-in-sequence delivery system used for conventional components. Specialized battery handling equipment is required to safely transport and install the high-voltage packs, which are typically mounted beneath the rear seat or trunk floor. Technicians working in these zones receive additional safety training and wear insulated gloves, tools, and personal protective equipment. The factory floor is also reconfigured to include voltage-safe testing bays, where hybrid Civics undergo electrical system calibration, battery charge verification, and inverter diagnostics before leaving the plant. Furthermore, Honda is increasingly experimenting with modular EV production cells, small, independently operable lines dedicated to electric vehicle production. While not yet widespread for Civic manufacturing, these modular cells are being piloted as scalable units that can be added to existing facilities as EV demand grows. Their flexible footprint and self-contained operation allow them to be spun up quickly in response to market shifts. There's also a growing presence of simulation-driven design in the manufacturing pipeline. Before a new Civic variant ever hits the factory floor, it is built virtually inside a high-resolution, physics-accurate 3D model of the plant. Engineers can simulate every weld, fitment, fastener torque, and wiring route before any physical part is produced. These simulations help identify potential interference issues, ergonomic challenges, or inefficiencies long before they reach real workers or robots. The result is faster model ramp-up, fewer line stoppages, and improved first-time quality. Even the training of plant staff is evolving. New workers learn procedures not just from manuals or trainers, but through augmented reality overlays that guide them step by step. Wearing AR glasses or using tablets, they can see animated instructions projected onto real parts, highlighting the correct bolt, identifying the right clip location, or warning about torque sequence. This immersive training dramatically shortens the learning curve and reduces mistakes. Through all of these innovations, sustainable processes, global synchronization, powertrain diversification, and smart manufacturing technologies, the Honda Civic continues to set the standard for what a mass-market, high-efficiency automobile production line can achieve. And it does so not with gimmicks or short-term fixes, but with systems thinking, scientific rigor, and decades of accumulated expertise. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors armed with light panels, bore scopes, and digital checklists reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture. a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro-adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer Gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Adidra, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of two-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process, frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large subassemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. The story of how a Nissan vehicle comes to life begins long before the first bolt is tightened or the first body panel is stamped. It begins in silence, inside vast facilities where architecture meets engineering precision. where design blueprints evolve into physical realities, and where automation and human craftsmanship converge in harmony. To understand how a Nissan car is assembled in a modern manufacturing plant, we must take a patient and measured walk through the process, beginning with the raw materials and the foundations of the factory environment itself. First, consider the raw ingredients. Unlike a loaf of bread or a bottle of juice, which may have fewer than a dozen components, a modern automobile contains tens of thousands of individual parts. These range from large body components to microscopic electronic sensors. Nissan vehicles are not built from a single supply chain, but from a sprawling network of global and regional suppliers. Raw steel, for example, is sourced from specialized mills that provide sheet steel of specific thickness, tensile strength, and corrosion resistance. These sheets often arrive in enormous coils, weighing several tons, each destined for a unique use, from structural frames to exterior body panels. But the metal itself isn't the only foundational ingredient. Aluminum is another critical player, especially in Nissan's push for lighter vehicles with improved fuel economy. Lightweight aluminum alloys are used in engine components, suspension arms, hoods, and doors. These materials arrive at the plant in various forms: flat sheets for stamping, extruded rods for machining, or even pre-formed castings for precision fitting. Plastics and polymers also play an indispensable role. Injection molded dashboards, center consoles, air ducts, bumper fascias, and even fuel tanks all depend on a continuous flow of petrochemical-derived resins. These arrive in pelletized form and are stored in high-capacity silos near the molding departments. Glass, rubber, wiring harnesses, textiles for seat upholstery, and electronics like sensors and infotainment systems all make up the broader raw material inventory. These are housed in precisely organized warehousing systems that operate using real-time inventory algorithms to maintain just-in-time delivery flows. Before any of these materials are touched, the factory environment itself must be primed. A Nissan plant is not just a series of conveyor belts and robotic arms. It is a living, breathing system engineered to the millimeter. The entire facility is divided into zones: stamping, body shop, paint shop, trim and chassis assembly, engine assembly, final testing, and outbound logistics. Each zone is temperature controlled, dust regulated, and equipped with fail-safe systems to ensure maximum uptime and worker safety. Let's begin with stamping, the first major transformation of raw material into recognizable vehicle form. The flat steel or aluminum coils are unspooled into long sheets, which are cut and fed into stamping presses. These aren't ordinary presses. They are massive hydraulic or servo-driven machines, each the size of a small house, capable of exerting thousands of tons of pressure in a single stroke. A typical press line consists of multiple stages. The first shapes the rough outline, the next adds structural reinforcement lines, and subsequent dies form the precise contours required for hoods, doors, fenders, and roofs. Each die set is a marvel of engineering, precision cut from tool steel, and maintained under strict tolerances. They are swapped out by automated systems depending on the vehicle model being produced. The forming process must be immaculate. Even a tiny wrinkle or deviation in the sheet metal can cause a cascade of issues downstream. For this reason, stamped panels are visually and dimensionally inspected using laser-guided scanning arms that map the surface of each piece in 3 dimensions, comparing it to digital blueprints accurate down to fractions of a millimeter. Once the panels pass inspection, they are automatically stacked and routed to the next zone, the body shop. This area represents one of the most robotics-intensive sections of the plant. Here, high-precision robotic arms work in orchestrated sequences to weld the stamped components together, forming the skeletal structure of the car, also known as the body in white. This name refers to the unpainted raw metal form of the vehicle before it is sent to the paint shop. To build a car's body with millimeter accuracy, Nissan uses jigs and fixtures that align each piece into place before welding. The majority of the welding is done via resistant spot welding, in which two electrodes press against a metal panel and send a high current, low voltage electrical pulse through it, melting the metal at the contact point to form a durable weld. A typical car body will undergo thousands of such welds, and each weld point is tracked in a centralized database, ensuring quality consistency across every unit. However, not all joints are welded. In strategic areas where welding might introduce too much heat or stress, such as near thin aluminum panels or multi-material junctions, Nissan uses structural adhesives and flow drill screws. Structural adhesives bond dissimilar materials together with incredible strength, while flow drill screws are self-tapping fasteners that create their own hole during insertion, eliminating the need for pre-drilled pilot holes. These innovations not only reduce weight, but also improve crashworthiness and reduce manufacturing cycle time. Robotic vision systems equipped with infrared and laser sensors ensure that each weld, screw, and bond is placed with pinpoint accuracy. Human technicians oversee the process, intervening only when a discrepancy or anomaly is flagged by the system. This collaboration between machine and operator defines Nissan's approach to manufacturing. Automation, where it boosts consistency and speed. Human touch, where judgment and adaptability are required. At this stage, the vehicle body still lacks color and character. It resembles a raw metal shell, cold, industrial, and devoid of personality. That all changes when the body in white moves to the paint shop, which is perhaps the most climate-controlled and sterile part of the plant. Before the vehicle even sees a drop of paint, it must undergo surface preparation, which begins with a multi-stage chemical bath known as the pre-treatment process. The body is first submerged in large vats of alkaline cleaner to strip away oils, residues, and metallic debris from previous operations. Following this, the body enters successive baths of rinse water, deionized water, and eventually a phosphate solution that chemically etches the surface. This phosphate layer provides corrosion resistance and improves paint adhesion. All of this is conducted using massive hoists and carrier systems that dunk and rotate the body at precise angles to ensure total coverage inside and out, including hidden cavities and internal seams. Next, the body is moved to the electrode deposition tank, or e-coat bath. Here, the entire shell is submerged in an electrically charged solution containing water-based epoxy. By applying a positive electrical charge to the vehicle and a negative charge to the tank, the paint particles are attracted and bonded uniformly to the metal surface. The result is a perfectly even, rust-resistant primer layer that coats every inch of exposed and hidden metal, forming the foundation for the subsequent layers of base coat and clear coat. This e-coated shell is then baked in a high-temperature oven to cure the primer. The body is carefully cooled afterward, and only then is it ready to receive its final paint layers, which we'll delve into in greater detail in the next segment. After the e-coated body is fully cured and cooled, the shell is directed into one of the most visually impressive parts of the manufacturing process, the paint shop. This area is entirely climate controlled, with tightly regulated humidity, temperature, and air purity. Any dust, hair, or particulate matter introduced at this stage could compromise the flawless finish expected of a Nissan vehicle. For this reason, all air entering the paint shop passes through high-efficiency particulate air filtration systems, and many areas operate under positive pressure to push contaminants away from the vehicle surfaces. The first phase in this stage is the application of the base coat, which gives the vehicle its recognizable color. Robotic paint arms, mounted on programmable tracks, glide gracefully along the length and height of the car. applying atomized paint in multiple passes. These robots are equipped with electrostatic sprayers, which charge the paint particles to ensure they adhere evenly and efficiently to the grounded car body. This process not only ensures a uniform coating, but also reduces overspray and environmental waste. Each model has its own programmed paint trajectory, accounting for variations in body shape and surface geometry. High traffic areas, like bumpers and door edges, may receive additional coats for added durability. Nissan uses waterborne paints to minimize volatile organic compound emissions, a key part of their environmental stewardship commitments. After the base coat is applied, the vehicle enters a controlled flash-off zone where the solvents are allowed to evaporate under gentle heat and airflow before the next layer is applied. Once the base coat is dried, the vehicle proceeds to receive its clear coat layer. The clear coat is a transparent, high-gloss, protective layer that not only enhances the visual depth of the color, but also shields the paint from ultraviolet radiation, road debris, and environmental contaminants. Like the base coat, it is applied robotically with fine control, and afterward, the vehicle passes through a large baking oven where the clear coat is cured at high temperatures for a precise amount of time. When the vehicle emerges from the curing oven, it gleams with a showroom quality finish. But this stage is not the end of the paint journey. Human inspectors take over here. Under intense overhead lighting, trained technicians visually and tactilely inspect each surface, feeling for imperfections and searching for inconsistencies. Small flaws, like dust nibs or uneven orange peel texture, are meticulously polished out, using ultra-fine sandpaper and buffing tools. This hands-on quality check ensures every painted body meets Nissan's cosmetic and durability standards. Now painted and gleaming, the body is transferred to a storage buffer zone while it awaits further assembly. These buffer systems are often automated, with conveyors and elevators storing completed bodies in multi-level racks, sorted by production sequence to ensure that the correct vehicle body matches the correct chassis and engine components downstream. Meanwhile, deep inside another part of the plant, an equally sophisticated and critical process is unfolding: the engine assembly. Nissan builds many of its engines in-house, often in the same complex as the final vehicle assembly line. These engine shops operate with surgical precision, combining cleanroom practices with high throughput automation. Engine production begins with core components: the cylinder block, crankshaft, cylinder head, camshafts, pistons, and connecting rods. The raw castings for these components are typically received from external foundries and then machined in-house. Large CNC machining centers mill the cylinder bores, bearing journals, oil galleries, and mounting faces with micron-level precision. Robots move castings between operations, and automated coordinate measuring machines verify dimensions at each stage. Each cylinder block is washed and deburred, then moved to the sub-assembly line. The crankshaft is inserted into the lower block and supported by main bearings, with torque-controlled machines tightening bearing caps to exact specifications. Pistons and connecting rods are assembled and inserted into the bores, connected to the crankshaft via piston pins, and rotated through their full stroke to verify smooth movement. The cylinder head, which contains the intake and exhaust valves, valve springs, and camshaft journals, is assembled next. Once the valve train is complete, the head is placed on top of the block and fastened with head bolts torqued in a precise sequence. Camshafts and timing components are installed, and the engine is rotated again to ensure timing alignment. What makes Nissan's engine assembly lines unique is their level of integration between automation and manual craftsmanship. While many of the tasks, like bolt tightening, parts insertion, and lubrication, are done by robotic arms or torco wrenches mounted on manipulators, human technicians are constantly monitoring alignment, oil sealing surfaces, and small tolerance adjustments. Certain high-performance or hybrid powertrains even require hand assembly by specially trained master technicians. Each completed engine undergoes a series of tests before moving forward. Cold testing stations spin the engine using external electric motors to verify internal friction, pressure buildup, and sensor communication, all without firing a single drop of fuel. Any deviation from the norm triggers a quality control flag, removing the unit for further inspection. Parallel to the engine line, transmissions are assembled using similar methodologies. Whether it's a continuously variable transmission, a manual gearbox, or a dual clutch system, each transmission unit undergoes assembly with exacting precision. Gear stacks, clutch packs, torque converters, and electronics are pieced together in sequences governed by computer-guided workstations. Like engines, each transmission is cold tested and electronically validated before release. As the engines and transmissions reach completion, they converge on the powertrain marriage station, a section of the plant where the powertrain is physically combined with the vehicle chassis and body. But before we reach that critical moment, we must pass through the trim and chassis assembly line, where the empty painted shell slowly transforms into a functional car filled with thousands of components. Before any parts are added, the painted body shell is prepped by attaching sound deadening pads and insulation materials. These are critical for reducing noise, vibration, and harshness, often referred to as NVH characteristics, and are strategically placed on the floor, inside door cavities, and along the firewall between the engine bay and cabin. Next, the vehicle enters the trim line. Here, the interior comes to life. Wiring harnesses are the first components installed, snaking through every crevice and corner of the vehicle. These harnesses are complex bundles of electrical wires, connectors, and terminals, enabling everything from headlight operation to GPS functionality. Depending on the model, there may be miles of wire bundled into various looms. Installers use routing guides and retention clips to fasten these bundles into the frame with impeccable consistency. Once wiring is in place, the dashboard, HVAC system, pedals, steering column, and electronic control modules are installed. These components arrive pre-assembled in modules to improve efficiency and accuracy. Operators use mechanical lifts and alignment jigs to position the large dashboard unit into the front of the cabin. Screws are torqued automatically, and alignment pins ensure everything fits perfectly. Seats, carpets, door panels, airbags, and interior trim components are installed in a choreographed sequence. Workers use rolling stools and robotic assist arms to move around the vehicle efficiently, guided by digital work instructions displayed at each station. Cameras and sensors verify part presence and correct orientation. Each vehicle configuration, whether leather or cloth, manual or electric seats, right or left-hand drive, is tracked digitally and updated in real time to prevent errors. While this is happening, another line is assembling the vehicle's chassis modules. This includes suspension assemblies, brake lines, steering gear, fuel tanks, and axles. These are pre-built into front and rear subframes that can be quickly bolted to the vehicle in a marriage station. The subframes are transported via automated guided vehicles that navigate the plant floor using magnetic strips or laser-guided navigation. The marriage station is more than just a mechanical juncture. It's a moment of transformation. Up until this point, the vehicle has existed as a painted shell, fully trimmed on the inside, but motionless and lifeless. Meanwhile, the engine, transmission, and chassis have been independently assembled, inspected, and prepared. Now, all these major systems converge in a single, highly orchestrated step that literally brings the vehicle to life. The process begins with the body shell being lowered from an overhead conveyor or scissor lift system onto the rolling chassis unit, which includes the engine, transmission, front and rear suspension, axles, and exhaust system. To align both structures perfectly, alignment pins, sensors, and robotic positioning systems are used. These ensure that mounting points for the subframes, powertrain supports, and drive shafts line up with millimeter-level accuracy. Torque-controlled robotic arms then secure bolts through carefully designed mounting points to bond the body and chassis into a single integrated structure. Once the powertrain is secured, technicians connect vital systems that bring the car's components into communication with each other. Fuel lines are attached from the tank to the engine. The exhaust manifold is mated to the underbody exhaust system. Brake lines are connected to the master cylinder and calipers, and the steering column is physically linked to the rack and pinion assembly. Electrical connectors from the wiring harness are snapped into their respective control modules on the engine and transmission. These quick connect systems are designed for both speed and reliability, allowing each connection to be completed in seconds, but still capable of enduring thousands of hours of vibration, moisture, and thermal cycling. With the vehicle now resting on its permanent chassis, the next step involves installing the wheels and tires. These assemblies are often pre-mounted and balanced at a separate tire center. Wheels are aligned on automated carriers and positioned next to each vehicle on the line. A robotic wheel installer or pneumatic torque wrench system fastens each lug nut in a star pattern, applying precisely calculated torque values to ensure even stress distribution across the wheel hub. This level of precision is essential not just for safety, but also to avoid issues such as uneven brake wear or tire vibration later on. With wheels in place, the vehicle is now fully grounded. It rolls off the marriage platform and moves on its own wheels for the first time. This moment is symbolically significant. It's the first time the vehicle exhibits mobility, but it's still not ready to run. Several fluid systems must now be filled and primed. The fluid fill area is a long stretch of the assembly line where dedicated stations automatically or semi-automatically fill the car with all necessary operating fluids. This includes engine oil, coolant, transmission fluid, brake fluid, power steering fluid if applicable, and windshield washer solvent. Each fluid has its own robotic fill nozzle mounted on articulated arms that connect to service ports with leak-free seals. The systems behind these nozzles monitor flow rates, fluid volumes, and pressure levels during the fill process. If a sensor detects a slow fill rate, potential air bubble, or leak, the system will automatically flag the vehicle for inspection. Coolant systems are pressurized and tested for leaks. Brake lines are vacuum bled to remove air and ensure proper hydraulic function. This is a critical stage where even a minor error could result in a major safety issue down the line, so every fill operation is closely monitored and logged in the vehicle's digital production record. After fluids are filled, the vehicle moves into the electrical initialization zone. Here, battery packs are installed, either traditional 12-volt batteries or high-voltage systems for hybrid or electric models. Once power is connected, the Central Electronic Control Unit, or ECU, is activated for the first time. This moment is often referred to as the initial software boot. It's the digital awakening of the vehicle when thousands of control modules across the car begin talking to each other for the first time. Diagnostic tools connect to the onboard diagnostic port and run a full check of the vehicle's electrical and software systems. Every sensor, actuator, light, motor, and module is tested for proper operation. Software is flashed or updated as needed, depending on the production sequence and region of delivery. The vehicle is now a networked system, with the ECU serving as the brain, overseeing everything from throttle control to driver assistance systems. Once the electronics are live and fluid systems primed, the engine is ready for its first start. This first ignition is more than symbolic, it's a functional validation. At a designated startup station, Technicians press the ignition button or turn the key for the first time. The engine roars to life, monitored by sensors that check for oil pressure, fuel system integrity, idle speed, and exhaust emissions. On hybrid or electric models, this step includes motor calibration and verification of battery charge levels. After the vehicle starts successfully, it proceeds to the alignment and calibration zones. Here, specialized machines verify that the wheels are aligned to factory specifications. Cameras and laser-based alignment systems measure camber, toe, and caster angles in real time. If any value is out of tolerance, the system automatically adjusts suspension linkages or control arms using powered adjustment tools. At this stage, cameras, radar sensors, and LiDAR modules are also aligned. These advanced driver assistance system components must be perfectly calibrated to ensure accurate lane keeping, adaptive cruise control, and emergency braking functions. Large panels with printed targets are positioned around the vehicle, and specialized cameras mounted on robotic arms adjust sensor aim and focus using software-controlled procedures. Once alignment is verified, the vehicle enters the dynamic test track area within the factory. This is an indoor or covered track designed to simulate real driving conditions at low speeds. The car is driven over bumps, through slalom curves, and across vibration plates. Brakes are applied at various intensities. Steering feedback is tested, and transmission shifts are observed. For EVs, motor torque and regenerative braking performance are measured. Trained drivers listen for abnormal sounds, vibrations, or behaviors. Any deviation from expected performance sends the vehicle to a diagnosis bay for further investigation. Vehicles that pass this functional road test move forward to water leak testing. They enter a sealed booth where a controlled shower simulates a heavy downpour. Water jets spray the vehicle from every direction for several minutes while technicians observe from inside the cabin. Any sign of water intrusion leads to immediate inspection and resealing. At this point, the vehicle is mechanically and electronically complete. What remains is finishing, final trim pieces, protective coatings, detailing, and inspections. Workers install badges, model emblems, VIN plates, tire pressure stickers, and other regulatory labels. Plastic protective films are applied to touch surfaces, such as door sills and infotainment screens, to prevent scuffing during transport. Some factories even spray a fine protective wax on the underbody and exposed metal areas for added corrosion resistance during shipment. A final quality audit takes place before the vehicle is cleared for shipment. This audit involves a checklist that covers over 300 inspection points: paint quality, panel gaps, door alignment, trunk closure force, hood latch function, seatbelt retraction speed, HVAC operation, infotainment interface responsiveness, and much more. Every light, switch, lever, and button is activated. Even the smell of the cabin is considered. It must match Nissan's strict standards for interior air quality and finish. Vehicles that pass this rigorous final inspection are driven a short distance to the shipping yard, where they are staged based on destination and production date. From here, they will be loaded onto multi-car transport trucks, rail cars, or roll-on/roll-off cargo ships, depending on their final market. While the sleek vehicles rolling off the final inspection line might seem like the pinnacle of the process, the truth is that the visible assembly is just the surface of a far more intricate system humming in the background. Beneath the polished robotics and synchronized welds lies the real engine of Nissan's manufacturing philosophy, its logistics and supply chain network. Every bolt, bracket, circuit board, and carpet panel that enters the Nissan production line must arrive at exactly the right time, in the right quantity, and at the right location. Any deviation, even a late shipment of a single component, can grind an entire production line to a halt. That's why Nissan operates on the principles of just-in-time and just-in-sequence production. Just in time, or JIT, means that components are delivered to the factory floor precisely when they're needed, not days or weeks in advance. This minimizes on-site inventory, reduces storage costs, and prevents parts from becoming obsolete or damaged. The process starts with Nissan suppliers, many of which operate their own mini factories or warehouses within a short radius of the main plant. These are known as supplier parks or vendor villages, and they play a crucial role in facilitating rapid part delivery. Within these supplier parks, Tier 1 vendors receive real-time signals from the Nissan plant via an integrated data exchange system. As a vehicle moves down the line and specific parts are consumed, such as a steering wheel or instrument cluster, the inventory software triggers an automatic order for replenishment. This order is sent instantly to the supplier's production line or warehouse, prompting them to pack and ship only the exact number of units needed. The goal is zero excess inventory. Materials often arrive in reusable shipping containers, pre-sorted for each specific car build, which are then returned for reuse. But JIT alone isn't enough for modern car manufacturing. Nissan also uses just-in-sequence or JIS logistics to match parts not only to the time of arrival, but to the exact vehicle configuration. Consider two vehicles moving down the line back to back. One may be a red crossover with black leather seats and a premium audio system, while the next could be a white base model with cloth interior and fewer features. The parts arriving at each station must match these exact builds. To achieve this, every car on the line is tracked by a vehicle identification number or VIN and a build manifest stored in the central production system. As the car enters each work cell, scanners and RFID tags identify it, prompting the delivery of precisely the right parts for that configuration. Automated guided vehicles, or AGVs, often carry these parts from the warehouse to the line, moving along predetermined tracks, or using laser navigation systems to avoid collisions and delays. These AGVs are programmable, flexible, and highly reliable. Some Nissan plants have hundreds of them in constant motion, shuttling dashboards, doors, engine modules, seats, and even air conditioning units. Each AGV is linked to the factory's Manufacturing Execution System, or MES, which manages scheduling, tracks the position of each vehicle in real time, and issues movement commands based on production needs. To make sure the right parts are always on hand, Nissan employs Kanban systems, visual signals, often in the form of barcodes or RFID tags, that are attached to each part's bin. When a bin is emptied at the line, the Kanban signal is scanned and sent to the warehouse, triggering a restock. In some plants, drones or robotic arms handle the physical movement of bins in the parts warehouse, pulling from high-density racking systems where parts are stored based on velocity and frequency of use. At the heart of all this is data. Nissan's factories are built around Industry 4.0 principles, meaning they are digitally interconnected, sensor-driven, and algorithmically optimized. Every robotic weld, torque wrench operation, fluid fill, and software update is logged in real time into a central cloud-based system. This system not only stores quality assurance data, but also enables predictive maintenance. If a welding robot begins operating at slightly higher amperage than normal, or if a torque wrench shows signs of calibration drift, the system can predict failure before it happens and alert technicians to intervene. This proactive approach avoids costly downtime and ensures that every vehicle produced meets consistent quality standards. The data also flows upward to regional headquarters and global management teams, allowing executives to monitor production volumes, part consumption rates, and labor efficiency from anywhere in the world. In terms of factory layout, Nissan designs its plants using modular zones, where each zone focuses on a specific function but remains physically and digitally linked to adjacent ones. These zones are often arranged in a U-shaped or serpentine flow, allowing for compact, efficient use of space and easy transfer of vehicles from one stage to another. Overhead monorails, automated elevators, and conveyor belts link the zones, while overhead digital screens and projection systems guide workers on each task to be performed for each car. Automation plays a dominant role but is not total. Human workers are still critical for tasks that require dexterity, tactile feedback, or judgment, such as installing fragile interior trim, adjusting panel gaps by hand, or performing final visual inspections. Nissan emphasizes human-machine collaboration, training its workers not only to install parts, but to manage robotic systems, interpret diagnostic data, and lead continuous improvement initiatives. To empower its workforce, Nissan has established Kaizen programs in every plant, small, team-led groups that regularly review their own work processes and propose enhancements. These improvements could involve ergonomic tool redesigns, reorganization of workstation layouts, or software refinements in part scanning systems. Suggestions are submitted daily, reviewed weekly, and implemented rapidly when proven effective. This bottom-up approach to optimization not only improves efficiency, but fosters a culture of ownership among workers. Alongside efficiency, sustainability is also a growing focus. Nissan's plants are increasingly powered by renewable energy sources, including solar panels, wind turbines, and energy recovery systems that capture waste heat from ovens or motors. Many facilities employ closed-loop water systems for cooling and paint booth operation, significantly reducing freshwater consumption. Waste materials like scrap metal, used oils, and excess plastics are sorted and recycled through dedicated processing centers on-site or nearby. Even the vehicle's logistics post-production are managed with environmental and efficiency goals in mind. Once a car is approved and staged in the shipping yard, a transportation management system determines the optimal delivery method based on destination, vehicle type, and urgency. Railcars are loaded using automated platforms, and cargo ships, often managed by Nissan's own fleet division, use roll-on/roll-off ramps to drive vehicles directly aboard with minimal manual handling. To minimize carbon emissions, vehicle loads are planned to eliminate empty return trips, and shipment routes are optimized to reduce travel distance and idling. In some markets, regional distribution centers are outfitted with charging infrastructure, allowing electric vehicles to be shipped at lower charge levels and topped off closer to the final dealership, reducing battery degradation during transport. So while the final vehicle may be the most tangible result of the process, the true marvel lies in the orchestration behind it. The invisible threads of data, logistics, robotics, and human expertise that keep each Nissan plant operating like a symphony. Every second, every motion, every part is tracked, timed, and optimized. With the vehicle fully assembled, tested, inspected, and polished, it is driven out of the factory's final inspection bay and onto a staging lot, a large, open-air shipping yard arranged with geometric precision. Here, vehicles are grouped based on model, trim level, destination region, and transport mode. While the car is now complete from a manufacturing perspective, the post-production logistics chain has only just begun. At this point, each vehicle carries a barcode or RFID tag that identifies every step of its production history, component list, software version, and destination. This digital tag continues to be scanned at each stage of post-factory handling, creating a living data trail that accompanies the car until it reaches the dealership, and sometimes beyond. From the staging lot, most vehicles are loaded onto specially designed transporters. These can be multi-deck car carrier trucks, capable of hauling up to 10 vehicles at once, or in high-volume markets, they may be driven directly onto rail cars. In coastal or international markets, vehicles are loaded onto roll-on/roll-off cargo ships, which are essentially floating multi-level garages where vehicles are driven aboard by professional operators and parked in precisely assigned locations. These transport decisions are based on an algorithmic system that weighs time to delivery, vehicle demand forecasts, fuel efficiency of transport mode, and cost. For example, a vehicle destined for a high turnover dealership in a major metro area might be prioritized for truck transport to shave days off delivery time. Meanwhile, vehicles going to remote or rural areas may be consolidated into rail or sea shipments for efficiency. As the vehicles leave the factory premises, they remain under Nissan's logistical control via a global transportation management system. This platform allows central and regional teams to track every shipment in real time, identifying bottlenecks, delays, or weather-related issues that might impact delivery. The system also manages estimated time of arrival, updating dealerships with live delivery windows so they can prepare for intake, inspection, and customer scheduling. Once the vehicle arrives at a regional distribution center, or RDC, it undergoes what is known as dealer preparation or pre-delivery inspection. These centers act as the bridge between the factory and the dealership showroom. The goal here is to ensure that every vehicle arrives in pristine condition and is fully ready for customer handover. The first step in dealer prep is a transportation damage inspection. Technicians walk around the vehicle with inspection checklists and tablet-based software, documenting any scratches, dings, fluid leaks, or scuff marks that may have occurred during transit. Although the entire logistics chain is designed to minimize movement and reduce risk, minor damage is still possible during loading and unloading. In such cases, paintless dent repair, polishing, or even panel replacement may occur before the vehicle continues downstream. Next, the vehicle enters a detailing bay where it is washed, cleaned, and visually enhanced for showroom readiness. Protective shipping films, the white plastics that cover door edges, hood panels, or infotainment screens, are removed, and the vehicle's interior is vacuumed, glass polished, and tires shined. In cold climates or during seasonal transitions, winter or all-season tires may be mounted if requested by the dealer or customer. Following cosmetic detailing, technicians perform a functional validation. This includes starting the engine, checking dashboard lights, updating software to the latest available version, confirming proper tire pressure, topping off fluids if necessary, testing the infotainment system, verifying remote key fob operation, and ensuring all driver assistance features like lane departure warnings, adaptive cruise control, or rear view cameras are fully operational. Once complete, the vehicle is assigned to a dealer stock list and released for final delivery. In many cases, dealership staff will come to pick up the vehicle directly from the RDC. In others, it will be trucked the final leg of the journey, often no more than a few hundred kilometers, to arrive on the dealer's lot. Even this final trip is tracked and timed. When the car arrives at the dealership, it enters a final phase of human interaction. Sales and delivery staff may apply dealership branding, affix local license plate brackets, or even install optional accessories that were requested at the point of sale. Some dealers offer ceramic coatings, floor mat upgrades, custom badging, or window tinting. Value-added services that help personalize the vehicle for its future owner. Now, for the first time, the vehicle story intersects with the customer. Whether purchased in person or ordered online through Nissan's digital retailing platform, the buyer is informed that their vehicle is ready. Many buyers never realize how recent the final factory steps were. In many cases, less than 10 days separate the moment the last bolt was torqued in the factory from the moment they received the keys. Before handing over the vehicle, most dealerships will perform a customer delivery walkthrough. This involves demonstrating how to use all key systems, pairing a phone with Bluetooth, adjusting seat memory positions, configuring driver profiles, navigating the touchscreen interface, and explaining the vehicle's service schedule. For electrified vehicles, staff walk customers through charging protocols, estimated range behavior, regenerative braking modes, and home charger options. But Nissan's involvement doesn't end once the keys are handed over. Every vehicle sold is still tethered to the manufacturer's digital service infrastructure, which includes remote diagnostics, over-the-air updates, warranty tracking, and predictive maintenance alerts. Modern Nissans, especially those with Nissan Connect, are equipped with telematics units that can transmit vehicle health reports, detect trouble codes, and even recommend service appointments. Through this connected system, Nissan can monitor the performance of entire vehicle fleets, identify recurring service issues, and even preemptively recall batches of vehicles if a defect is detected statistically. Dealerships receive diagnostic data in advance, meaning that when a customer drives in for service, the technician already knows what to expect and what parts may be needed. Additionally, every service performed at an authorized dealer is uploaded to a vehicle service history database, providing transparency for both the manufacturer and future resale. This connection between factory, dealer, and customer creates a full lifecycle data loop that supports ongoing quality improvements and customer satisfaction. Behind the scenes, Nissan also uses customer feedback and market analytics to inform future production. Purchase patterns, option uptake, color popularity, and return maintenance data all feedback into the company's planning divisions. This helps refine inventory decisions, forecast parts demand, and even shape the designs of future models. For example, if a particular trim package is consistently chosen in combination with a certain wheel option or driver assistance suite, that configuration may be bundled into a new trim level to streamline ordering and improve plant efficiency. Likewise, if a specific infotainment issue is repeatedly flagged in customer feedback, Nissan's engineering and software teams are notified and tasked with investigating. In this way, every Nissan vehicle is not just the product of a one-time manufacturing event, but the node in an ongoing relationship between machine, human, data, and organization. Each car that leaves the factory becomes an extension of Nissan's global strategy, a testbed for improvement, a data source for refinement, and a living example of manufacturing precision. The customer may never see the Weld robots, the e-coat tanks, or the AGVs that moved their dashboard into place. But within the tactile feel of the gear shift, the gentle click of a climate control button, or the quiet hum of the motor lies the fingerprint of an entire industrial ecosystem. The Nissan vehicle is the visible result of millions of invisible decisions, flawlessly synchronized in time and space.